Good morning. Today we are going to talk about Module 3 Dynamics of Fluid Flow, wherein we will start with Bernoulli's equation, which states that P upon rho g upon 2g stands for velocity head and Z stands for potential head or datum head. The summation of total energy of the system is supposed to be constant. This is Bernoulli's theorem or Bernoulli's equation, as you can call. Now, there are certain applications of Bernoulli's principle. We'll first discuss about venturimeter. The discharge through the venturimeter can be calculated using this formula CD A1 A2 root of 2GH upon root of A1 square minus A2 square. Actual is what is written here, and its unit is meter cube per second. And the term CD over here stands for coefficient of discharge. It has no unit as it is a ratio of same quantity. It is a ratio of discharge which is actually happening to the pipe to the discharge which you calculate theoretically. So Q theoretical is here. Its unit is meter cube per second. Now this is how the venturimeter looks like. Here you have your section 1. The diameter here is D1. At section 2 over here your diameter is D2. Say there is a manometer attached at these two ends. With the help of pressure taps you can connect the manometer here. This is the mercury which is in the manometer. As you can see, there is some fluid flowing through this pipe and hence through the venturimeter. So there will be some difference of fluid pressure at the section 1 and 2 which can be measured as a difference X over here. Now the venturimeter is divided into three parts. You have the first short converging end over here, as you can see. Then you have a small portion which is called as a throat and the long diverging end over here. Now since you know the diameter D1 and D2, using the formula A1 is equal to pi by 4 D1 square and A2 is equal to pi by 4 D2 square, you can calculate the area A1 and A2, which you can substitute in this formula, and you can get the value of Q actual. Known the value of CD, G is always known to you, 9.81, and the value of H can be calculated if you know the difference of this mercury level in the manometer. Now X is the difference of mercury level in the differential manometer mm of Hg. Now for calculating H, there are four cases which we are going to discuss. Now in that also there are two types, type A and B, wherein in type A we are going to say that the venturimeter is held horizontal, and in that you have first case when the liquid in the manometer is heavier than the flowing fluid. Now suppose if you have a liquid in the manometer which is mercury and the flowing fluid is say water, in that case you can calculate the value of H as X into SH upon SF minus 1, where SF will indicate the specific gravity of heavier liquid and SF will indicate the specific gravity of the flowing fluid. Heavier liquid here will be your mercury in the manometer, flowing fluid we have as water. It can be liquid or fluid as you can call it. Now S of heavier liquid here mercury is going to be 13.6 and S of flowing fluid here is going to be water, which is 1. So if you substitute in this formula you will get the value of H in terms of meter of water column. X is in terms of mm of mercury because the manometer is calibrated in terms of millimeter and the fluid we are using is mercury, so the unit will be millimeter of mercury. We are converting into meter of water column. Now we go to case 2. Say the liquid in the manometer is lighter than the flowing fluid. Say in your manometer you have air or oil whose specific gravity is lesser as compared to flowing fluid, say water. Now in this case your manometer cannot be a straight U manometer, it has to be an inverted manometer wherein your light liquid is subtended upward. Otherwise if you have a normal U tube manometer with gravity, then your heavier liquid will become a flowing fluid and then your heavier liquid will go and get accumulated in the manometer. So H is equal to X into S minus SL upon SF. SL is the specific gravity of the lighter liquid. Say it is air or it is some oil whose specific gravity is 0.8 or 0.9, and SF is going to indicate the specific gravity of the flowing fluid. Say your flowing fluid is water. So you can use this formula for calculating the value of H again in terms of meter of the water column because your flowing fluid is water and X is the liquid in the manometer. Now we will talk about type 2 when the venturimeter is inclined. When the liquid in the manometer is heavier than the flowing fluid. This is again the same case which we are taking up, only that your venturimeter is inclined. Now by inclined I mean at any angle of theta, and the theta can also be 90 degree. So apart from 0 degree, any other angle is included in theta. So suppose if I say when the liquid in the manometer is heavier than the flowing fluid, in that case you can calculate H as P1 plus rho g plus Z1 minus P2 upon rho g plus Z2. This is the part of Bernoulli's equation which is applied at section 1 and 2. So here H is equal to this formula. It can also be calculated by the same formula which you have used above, x into SH upon SF minus 1. Now again we take case 4. When your liquid in the manometer is lighter than the flowing fluid, then your H will be P1 upon rho g plus Z1 minus P2 upon rho g plus Z2. It can also use the same formula which you have already used, x into 1 minus SL upon SF. So this is the way of using the formula for calculating discharge of venturimeter.